To begin with, the idea of a Taylor polynomial of degree n for a function at 0 can be expressed in sigma notation. And so we need to determine the Taylor polynomial of degree n for f at 0. And this is therefore called the Maclaurin series. Okay, first question. Determine the Taylor polynomial of degree n of f at 0 and express it in sigma notation. Right, so this kind of a series is basically called the the Maclaurin series. Okay, if it's at 0. Right, so we're getting started now. We note that the function f of x is actually 1 divided by x plus 1. Why is it like this? Because the examiner gave it this way. It was given like this. Right. So what we do then, we write first the polynomial given. The next thing is we find the derivative of the polynomial. So the derivative is going to be x plus 1 to the minus 2. We find the second derivative, and it is exactly minus 1. And then there's minus 2 using the power rule. We're effectively using the chain rule of differentiation at this point. The third derivative, minus 1, minus 2, minus 3. Okay. Right. So we go on. Let's just find one more. The fourth derivative of the function is minus 1. Right, it is exactly minus 1. Right, so it's exactly minus 1. Then we continue. Minus 1, minus 3, minus 4 into x plus 1 to the minus 5. So we have f at 0 is 1. So if you replace 0, x by 0 in the f equation. Now in the f prime of 0 equation, you replace, and then it becomes minus 1. In the second, excuse me, derivative, what do we get? We get precisely that one. We get precisely 2. You can write it this way. This implies that the third derivative at 0, we replace x by 0 into the third derivative, and it becomes 6. We have the fourth derivative, which is equal to what? 24. Okay. Right, so we have these here. And then now, what is the formula for the Taylor polynomial? Right, so the formula for the Taylor polynomial can be written like this. So it is exactly t n 0 f of x. It is f evaluated at 0. It is f primed at 0 times x. This is the formula for the Maclaurin series, or Taylor at 0. So Taylor evaluated at 0, Taylor polynomial evaluated at 0 becomes, it's called Maclaurin. So Maclaurin just means at 0. And therefore, this is x squared out of 2 factorial. Okay, let me just include a little bit more. But the pattern is visible, but yeah, the pattern becomes very important when we do the R, because you need to be able to see the nth derivative. So now here we're going to have the fourth one, the fourth derivative, x to the fourth factorial. Okay, and then now we can just do essentially one more, which is the fifth. Yeah, because okay, I stopped at the fourth, so it's okay. Right. Um, I stopped at the fourth derivative, so it's fine. So you have so you have that. Okay. So now we have the following. Right. So we have this. Now we need to just do substitutions. And if we do, what do we get? We're getting t of f of x, t n 0 and f of x. What is f at 0? Is 1. This one here. F primed at 0 is minus 1. Double primed is 2. Triple primed is 6. Okay, let me write a nice one. Then simplify automatically, because the f double primed is 2, but 2 factorial is also 2. So this one you can just write it as x squared. Right, f triple primed is 6, but 3 factorial is also 6. So that's x cubed. F quadruple primed is 24, but 4 factorial is also 24. So this is just that. Right, so the pattern is visible and is very, very clear. Okay, there is a sign issue here. Right, the first one is positive, this one is negative, and then the 2 is positive, this one is negative, the 24 is positive. So the 6, it's going to be negative here. Okay, it's going to be negative at the cube. Right, it's going to be negative at the cube here. Right, so we have this, and then the fourth one is positive, and so on. And then you can see the alternation, so it's positive, it's negative. Oh, we can start saying it's positive at the beginning, negative, positive, negative, positive. We expect this one to be a negative. You can write it like that. You can also put a positive, but strictly speaking, it's going to be negative. Okay, so this one is going to be negative here. And then now you have this. Okay, what is the nth derivative of this? How will it behave? Here comes the little trick. Here comes the little trick. But you can see that when the power is 1, when the derivative is the first, an odd derivative, if you like, the order of the derivative being odd, so you get a minus 1. If it's 2, even number, it's positive. If it's 3, it's negative. If it's 4, it's positive. So in other words, it depends on some n. So it is some minus 1 to the power, minus 1 to the power n, x to the power n. Okay, so this is what we get. So in the end, then you have that this is r to the 0 minus 1 to the power r times x to the power r, like that. Okay, determine the Taylor polynomial of degree n, So the degree is indeed n because it stops at n, for f at 0. Expressed in sigma notation. We have expressed it in sigma notation, and there it is. Okay, so we've answered this question here. Next question. Right, so in this question, 6.2, we consider the same function. But now we're saying for all x that lies between 0 and 1 here, we have to show that, or we have that the limit as r approaches infinity of the remainder term is 0. And you need to show that we have these equal to 0 as a power series. Right. Right. Okay, continue. Solve this one. Yeah, need to just show that that is 0. Right, to show that it is 0, first and foremost, you need to look at the nth derivative. So f, what is this? Right, so we have that the nth derivative is what? Right, it's this one. Like the fifth derivative. What does the fifth derivative have? So the fifth derivative is going to stop at 4. Oh, the fourth derivative. Okay. Okay, let's just pause to generalize the derivative here. Right, so which means that if we are to look at the nth plus first derivative, and now if we decide to evaluate this derivative at x, what is it the same as? So you need to look at these here, 1, 2, 3, 4. So nth plus first, this. Then we have minus 1 to the power n. So minus 1 to the power n, okay? Too congested. Let me create a little bit of space here. So I'm trying to generalize this derivative from the pattern of the derivatives we're seeing. So we always do that when it comes to the Taylor polynomial. I mean, this at least in this module. So what is this here? Is minus 1. Okay, because you can see that it's minus, plus, minus, etc., etc. So the signs alternate. Let's look at the fourth derivative, which is a bit more detailed. Right, so if you multiply negative by negative is positive, negative by negative is positive. But obviously it is negative 1 to the fourth power. There are 1, 2, 3, 4 negative ones. So it is the fourth power, which is the fourth derivative. So it's going to be the same thing, so it's going to be the nth plus first derivative. So we need the nth plus first derivative. Okay, now if this is the fourth derivative, it's going to be 1, 2, 3, 4, because the third derivative stops at 3, the second derivative at 2, so the fourth derivative stops at 4, so it becomes n plus first factorial, like this. And then at the end of the day, we divide by x plus 1 to the nth plus first derivative for 0. Right, so now we have that. Okay, let's state that one. Enough. Okay, they did not ask us the blue part. The blue part, we're just generalizing the derivative there. Okay. Now let's continue and take this derivative and take it to the other side. So we remember from the previous page that this is the nth plus first derivative of the function x, of the variable x, excuse. So we saw that it is always -1 to the nth plus first. So we divide by nth plus, okay? Okay, you realize, excuse, that here, if it's 2 here, it is 3 there. So it's always one more. So this one is going to be 2. Okay, it's going to be 2. This one is going to be 2. Because if it's 4 there, it becomes 5 in the denominator. So it's n plus 2. So this one is going to be plus 2. Yeah, like this. Hey, now we normally evaluate this one at the nth plus first. N plus 1. And then it's c plus 1. Or we can write 1 plus c, replacing x by c. We understand at this point that this is true for the c we're dealing with always. Right, the c we're dealing with is a c that is less than x. Thus, so now there is now the r, the remainder term of degree n of the polynomial degree n at 0, associated with the function x, f of x. And this is therefore the same errors. So this is going to be the same errors. So you take the nth plus first derivative at c, which is x to the power n plus 1, which is divided by n plus 1. So what is f of n plus first derivative? Okay, so in other words, this is what we get. You multiply the n plus first derivative by x to the power n divided by n plus first factorial, and you have the absolute value there. Okay, have this. Right, this is therefore equals, what is the f plus, the f for n plus first derivative? Right. What is it the same as? Okay, so this is the same as, let's look at it very carefully. Right, if you take this and you put it into that, so it's going to be exactly n plus 1 factorial. We are taking this one, the f, exactly that. But now it is multiplied. You can have this one here, but it's going to be, the -1 is just going to dissolve to 1 because of the modulus. And now you also have the x to the power n plus first term divided by n plus first factorial. And then you also have here you can write 1 plus c or c plus 1 to the power n plus second derivative. Okay, right, so this is the same as n plus first derivative, n plus first derivative, x to the n plus first, then which is n plus 1. So what is all this here? What is all this here? So this is the same as, you can see, you have the x to the n plus, so you have the factorial here. Right, so you have that this one cancels this. And x divided by 1 plus c. And then which is exactly 1 plus c. Okay, so it simplifies exactly to that because you have the 1 plus c in the denominator has n plus 2, just one more 1 plus c factor. Okay. Hence, we obtain the following. Right, so we obtain Rn0 f of x is equal to what we got on the previous page. That one. So it's actually the modulus of x divided by 1 plus c to the power n plus 1, 1 divided by 1 plus c, means we have x element of the interval from 0 to 1. We have 0 less than c. The c lies between 0 and 1 because x always lies between 0 and 1 for this kind of series. From the notion of a geometric series from school, for the convergence of this series requires that our x lies between 0 and 1. And so if you take c, you add 1 to it, it's going to be bigger than 1. And that is to say, if you take c and you add 1 to it, it is bigger than x, and x is bigger than 0. Thus, x divided by 1 plus c will most definitely approach which is what we have here, will most definitely approach 0. But now I can write it nicely. Well, one likes a smarter way. We use the limit notation, but you can use the words. Right, that's the limit. Okay. Right here, so that's the limit is n approaches infinity. of the remainder term of the polynomial of degree n at 0 of the function f of x, limit n approaches infinity, um, 1 plus c, so as n approaches infinity, you have that this x is between 0 and 1, so it will approach 0. Okay, because this is a fraction. A fraction, the way a fraction behaves. So if you take the limit as n approaches infinity of a fraction, 1 over 3, fraction that's between 0 and 1 is like 0.3, for example, and you raise these to infinity. This is just an example. So you'd have that this is therefore you can write this is the limit as n approaches infinity. You can write as 1 over 3 to the power n. And then with n approaches infinity, this is 3 to the infinity. And what is 3 to infinity? It is infinity. 1 over infinity becomes 0. So that becomes 0. So the course is between 0 and 1. Okay, so this is just an example. Right, the conclusion therefore is that hence um hence the limit as n approaches infinity of Rn 0 f of x, this limit equals 0. And the question obviously was you have to show that this limit equals what? Equals 0. And we've just shown that. Now, the next thing is you need to write down the Maclaurin series for the function f of x on the interval 0 and 1. Let's write down the Maclaurin series. Right, so to write down the Maclaurin series, we already know that the function f of x is actually given as what? Is this one here? X plus 1. What we got at the beginning, that series was just the Maclaurin series. Because we wrote this function as 1 minus x plus x squared minus x cubed plus x to the fourth. Can continue with the pattern. After the negative is plus, so there's that alternation, but we saw that at the even powers, we had a plus. At the odd powers of x, it was negative. For it's an even number, there was a plus and so on. And therefore, the general term was because it's t n0 of f of x. So it's a polynomial of degree n at 0. So this therefore became that. Okay. So now we have right, so this is r equals 0. For this one, we can write r. Okay, so this one, just writing in terms of r. So normally we switch the n and the r around. The n is the order of the polynomial or the degree of this polynomial. And therefore, this one here stops it at minus 1 to the r, x to the r. And because for x between 0 and 1. Hey, this is what we get. Well, this is the Maclaurin series between 0 and 1. Okay, now the bracket, the parentheses in terms of that. Okay, the question obviously had round parentheses, so you can just maintain those for accuracy purposes. It's more accurate to put the round ones. Why? Because we want these to converge. So it's very correct to put the round parentheses here. So we have written that one just for 1 mark. So we had already done that. So yeah, no big deal. In 6.4, we need to use the Maclaurin series. In 6.3, to write that one as a power series on 0, 1, and then determine the power series for octant x. So at this point, you'd need 1 plus t squared. Use the Maclaurin series in 6.3 to write this one as a power series in the 0, 1 interval, or on the 0, 1 interval, and determine the power series for octant. Right, so there are a couple of things obviously we need to remember here, and you can just remember that the integral of the 1 over t squared plus 1 is octant. Right, first things first, let's remember the original series. Okay, I'll just write, you can write, yeah, you remember it, but okay, you have to recall that. Right, so we recall that, recall f of x is this. And this is the same as what? Well, so this will sort of imply that. That's not what I wanted to say. Okay, we got the series for 1 over that, so we can just write it out. So this one is the same as 1 minus x plus x squared plus, no, minus x cubed. Right, so we have the minus x cubed here. Plus dot dot dot. To the n, x to the n. Okay, so now you therefore have 1 over 1 minus t squared right, so you have that. Okay, this you can write in many ways, like that. You can write t squared or t to the 4th power, but you can write it like this, so that you can see the pattern. You can write to the 6th power, but you can write like this. T squared to the nth power. That's what we have. Okay. That's what we have. Right, so we have this. Okay, we have this. Moreover, we remember that this one was just minus 1 to the power r, x to the r 0 to Infinity? No. To n? I hope I didn't write infinity here. So used to writing infinity. Right, okay. Right. Obviously it stops at doesn't stop at infinity, please. Happy that I realized that. It stops at n. Wondering. Okay. There are more infinite series than finite ones that we study, so yeah. Right. Just checking where I wrote infinite series. Okay, here I wrote yeah, up to n. Okay. Right, so we have this. So the question therefore becomes, what is the series here? Um, so you have here up to r. T squared to the power r. Okay. So we have written the one over this. You can write like this. T squared plus 1 and 1 plus. Okay. All right. So use the Maclaurin series in 6.3 to write this one as a power series. We have written it as a power series. And then determine the determine the power series for arc10. Mm-hmm. That's something called the arc10. Arc10t is basically the integral from 0 to Mhm. Okay, this is also an error because this is t everything here. So this must be arc10t. You see, we're integrating a function of t, so you must get t plus c. Wondering why they wrote an x there in the question. So the arc10t, therefore, provided there was something missing here. No, there was nothing missing because there's a constant c. So I was thinking maybe when these were scanned, the limits of integration could not appear on the scanned version, but yeah, it can't be because it's plus c. So this was an integral that did not have limits of integration, so it was an indefinite integral. It was an indefinite integral. So now this one, now we come to the arc10t. Okay. Right, I want to mention therefore that these can be as arc10x. Right, just things, notations here. So it can be written as arc10x, this one. Right, can be written as arc10x. It's the integral from 0 to x, which is 1 divided by 1 plus t squared dt. Um, 0 to x. So the 1 of the 1 plus t squared, okay, Okay, I want to mention something here. Okay, this question obviously is saying we need to use the Maclaurin series from the previous page. We write this one as a power series. And so you need to understand that the power series obviously is an infinite series. Even Maclaurin is generally infinite. So this, we're going to make it infinite because of the word power series. Because power series are infinite series. So it was n, but I'll have to extend this now. Need to remove this. What am I going to do here? You need to go beyond the n. That's my point. So it doesn't matter what I do. We need more terms. Ah, okay. I need the cosine, I'm sorry. Right, so I need to extend that. So um the R. Hey, so you can go on here. There's a power series. Right now we're trying to integrate it, but now if we integrate it, you need to use the Maclaurin series, which was finite, but Maclaurin series generally are not, but it's just that they're not finite, they're infinite. So they become power series standard at zero. Um, those power series have a special name, Maclaurin. So we have these, but now we have this. So and determine the power series for arctan x. So from t we need to get arctan x. From t we need to get x. So we have t here, so the x can only be brought as a limit of integration. Okay, that's the point. But if it's brought as a limit of integration, then what is the 1 over t squared, etc.? It is the power series. So it is t squared here. So you have -1. Okay. So then you then have the integral. We have these. Okay. So this is possible, right? Then we can just integrate this one right now. So hence, you obtain the following. Octan x r equals 0 -1 to the r So let's find the integral of this now. And this is the infinite series, power series, right? -1 to the power r. Then now we find the integral of this. So it is 2 to the power twice r plus 1. We divide by this. And this now, you have 0 to x. Um, you have this. Okay. We have that. Okay, so we continue. What do we get out of these? Right, so we substitute the t by that. Substitute t by x. So it's going to be x to the power. Okay, which converges? For that. For the modulus of x smaller than 1. Okay. A very creative question from the examiner. A wonderful question that draws a distinction between power series and what we call a Taylor polynomial. Because you'll notice that determine the Taylor polynomial of degree n for f at 0, expressed in sigma notation. So you have that. Okay, we had the Taylor polynomial of degree n. So if it's of a finite degree, you can see the language the examiner uses. It's a Taylor polynomial. It becomes a polynomial than just a power series, because obviously you can see it's a polynomial of degree n. And then now it becomes in a power series when it is infinite. Okay, we have answered this question. We continue to practice, but yeah, I think that this question is very similar to what we know. Um, maybe I get another question. Um, did I get another question? I think. Okay, can practice, but yeah, it's very similar to what we've seen. Okay. I'll get another question additionally, but um, right. So we continue. But let's just practice the questions, because the reason why it is profitable to do these questions the way we're doing is because with the structure of the exam at UNISA, you cannot expect anything different anyway. So the structure is very much the same. So, and hence you are not going to be surprised by anything that is different, you know. You're not going to be surprised by anything that is different. Right. So We continue. Right, so 7.1, to state the criterion for a function f to be Riemann integrable. This is how we state it. We say let f be defined by, let f be defined by right, let f be defined by, at least on the interval, right, so at least on the interval, so let f be defined on AB, the closed interval AB, then f is Riemann integrable on AB if and only if and only if for every epsilon positive, there exists a partition P of AB such that UP minus LP is smaller than epsilon. Right, so we let f be defined on the closed interval AB, then f is Riemann integrable on AB if and only if for every epsilon positive there exists a partition P or of AB such that UP minus LP is less than epsilon. We give that statement of the criterion for the function f to be Riemann integrable on the interval AB. Right, obviously now going on to explain any notation used. Obviously the UP used in this case actually symbolizes the where. Okay. Right, where the UP right, where the UPN is the Riemann upper sum, and LP is the Riemann lower sum. Right, can be stated this way. And it can be stated with yeah, it's fine like this. So you can state it with the subscript n, but you can always state it as given there. Okay, because now when the difference between them is less than epsilon, It means, therefore, we are taking n to be very large. When n is very large, n approaches infinity, this difference is very small. Ultimately, we agree that if a function is Riemann integrable, then this must be equal. If they happen not to be equal, then it means a function is not Riemann integrable. What kind of a function would not be Riemann integrable? Let's look at an example. Okay, they did not ask us this, but okay, most of the functions we study are Riemann integrable because the function itself, the function themselves, um, need to be continuous. That is the primary condition. F of x is an example. This one did not ask this. 0, 1. When it's 0 when x is irrational and when x is rational. When x is rational and when x is irrational, it is 0. Okay. Right, so this function is a very important one. Right, this function is called the Dirichlet function. Right, this function is called the Dirichlet function. Right, so this function is called the Dirichlet function, and it's either 0, 1. This function itself is discontinuous, it's not continuous. Because it oscillates. It's 1, 0, 1, 0, 1, and so on. So that kind of thing. Not continuous. Okay, you can spend some time. This question quite never came at some point. Early around 2017, 2007, I think. Right. Well, this one is not Riemann integrable. F is not Riemann integrable. Okay, I think I'm going to spend some time on this at some point. It's not Riemann integrable. Okay. We can, I know we have learned this very much. I lost power, 2 minutes. I lost power. Okay.